Heaps and priority queues are a bit of a hybrid data structure where they act like a list. They're built a little bit like a tree and have several really useful real world uses, but are super important to other data structures down the line that you might come across because of the ability to selectively organize data on the criteria that has one focused goal. So, for instance, let's talk about the idea of paying your bills. So each month you have a stream of bills that come in, and they don't tend to come in all at once. You tend to get them through the month, and they don't tend to come in any specific order. They just show up whenever the bill, you signed up for the bill, or whatever the company decides the time to pay the bill is. But there's certainly a priority to paying your bills, especially when you have a limited amount of resources. I mean, if you're unlimitedly rich, you pay whatever bills you want to, and it doesn't matter. You never exhaust your funds. But for most folks, you have to have do some sort of money management around your bills, and I'm not just talking about your everyday bills, the things you'd like to do as well. Go on vacation or other eh, ways to spoil yourself or use your money beyond your basic needs. So we think about data structures. What would the best data structure be for paying your bills? Well, if we thought about a list, we'd be paying the bill we first received. That would be the one that most likely we would go through. The idea of first in, first out. So, is the oldest bill the best one to pay? I mean, if you've got the money, definitely. But maybe isn't always the case. Maybe the oldest bill I have, it could just be like a long desired dream to go on a worldwide tour, and it's also a very expensive bill that would take up other things. So the stack, what's is the most recent bill? Should I pay the most recent bill? Well, maybe. I mean, if my car bill comes in today, that's I definitely want to pay my car bill. It's important. But if I haven't paid my mortgage yet, well, maybe making sure my house is paid for is more important than my car. It depends. I mean, I need to pay for medicine right now, then that is a great thing to pay for right now. But it depends on what the most recent thing is. A set probably isn't going to work. Especially if I have bills of more than one kind. So if I get a credit card statement that has grocery bills three times, and it's my set says groceries, oops, I only pay one of those. That would just definitely be a problem. I would not be paying the groceries. Not the best analogy, but it works a little bit okay here. So none of these data structures are absolutely ideal because each one of them would require me to do some level of searching through the bills to figure out what the priority is. And so the priority queue actually stores the data based off of some notion of priority already. So let's explore this analogy a little bit further. So if we just see the bills coming in one at a time, our car bill, we buy some coffee, here's our cell phone, we go to the movies, hey, let's buy some plane tickets. Oh, then some groceries, get a car wash. Oh, nope, end of the month, now the mortgage, the rent is due. Um, and oh, the taxes come around occasionally too. Um, what order should we pay these in? Again, assuming limited resources. They're coming in at different times. Maybe we pay bills throughout the month. We might not do it, once a month. We just pay it as money comes available. So how do we choose, which one comes when? Well, we have to create some sense of priority. Now, there's no right answer to the sense of priority. It's up to the design of your app, and in this case, your personal preferences. But if we could rearrange this data storage to say, well, this is roughly speaking the things that I find to be more important. So I want to, make sure my house is paid for and I eat. I don't want the government coming after me, so I pay my taxes and I need to drive to get to work. Coffee, that's an important thing for me, and then maybe cell phone bills, go to the movies, get a car wash, and I do want to go on vacation someday, but maybe that's something that I save up for and wait until I have that extra burst of funds. So I know many people who basically budget based off of what's in their account. So of course there's other ways to plan. The analogy only goes so far, but in computing systems, um, if we don't have the longitudinal view of what's coming up, so let's just say I'm processing incoming text, then I need to have some help in doing that because I can only see what's available. So let's think about it this way. Priority queues give us a little bit of a variation to a list. When I insert, I add things to the list, but I rearrange the internal data structure in order to make sure the first things I'm getting out are the things of the highest priority. And when I remove, I always take the highest priority item first. Uh, at least in the standard, remove to go do work on it. There's also an option to remove the minimum because I need to just throw away something. I mean, if again, the analogy is if I don't have enough money, maybe I don't go on vacation. I'd take that off my list. I'm sorry, I'm not buying these tickets this month. Oh, I'm really broke. Well, I'm not getting my car washed this month. And so those things just kind of fall off the list as other more important, medical bills or something else comes up. So if you think of it in a computing sense, the easy answer for that is if your phone rings, whatever game you're playing on your phone, what other app that's a lower priority, it goes to the background. So a really useful computing solution for a priority queue is what processes are running, and the one that runs next is going to be based off of the highest priority. And you say, well, wait a minute, shouldn't it just interrupt? And it can, but you know, in computing senses, a long time for a computer to run something is sometimes 1/20th of a second. If your phone rings and it doesn't actually have that process pop up for a quarter of a second, that's faster than your reaction time. I mean, it's not going to make that big of a difference. And so in a quarter of a second, the computer could have swapped processes 15 times. And so it just says like when it swaps next, the next thing to pop up is the phone app because that's the most important thing to have happen. All right. Another example of looking at that is, like if you want to see like trending topics on Twitter. I don't know how it's implemented, but I could imagine that they could use a priority queue within that. You have all these tweets coming in, and the tweets theoretically have equal priority, but when you kind of start adding them up, we can see which ones are the trending topics, the hashtags in particular, and they can bubble up to the top. And so as you have a list of let's say a million tweets that come in every second or a minute or whatever that number is, but I only care about the top 10 of them. And so 10 of them maybe a human can remember, but let's say top 100 of them. And that'd be harder for us to remember. Well, a priority queue says, well, if this trending topic is in the top 100, we keep it. If something else comes in that has more numbers than is already out there, then one of those drops off of that priority queue. So we'll get to see a little bit more of this in action, but I want to give you a feel for why these are useful and what they can do. So they're both a idea of absolute priority of things that we can choose to sit down and deal with, like bills, which we're not normally inundated by bills, but in computing we often are. We have big, we're reading files, we're getting the information off the internet, and it's coming in faster than we can possibly hope to process it. We just can't remember all the stuff at once, and so this helps us tell what we should remember and focus on. So the foundation of a priority queue is this data structure called a heap. And so it organizes data by either the maximum values, where the highest values go first. So maybe my priority is 10 or 15 or 100, or like as we said, the trending topics. There's 1,000 people talking about this, or 10,000 people talking about this, or 8 people talking about this. And the 8 might fall off, not be important after a while. Or we can talk about the min, where the lowest ones go first. So I can say, DEF CON 1 and jobs, really important, are I think it goes up to 5. But anyway, the lowest priority might be assigned to number 1, their operating system, low level 1 jobs, or important apps like the phone is 2 jobs, and games are like 7 jobs, or something like that. So um, when we get into this, there is some organization to the heap, but the heap is not exactly a tree. As we move forward and look at the internal structure of this, it's going to look like at times a tree. Now, you may have you remember you may have studied a bunch of details on trees. I mean, I hope you have. We've talked about them a little bit here, but just remember that trees always organize the data where the left node, the left children, if you will, are always going to be less than, the right are always going to be greater than, than yourself. So a tree, you have a left-hand side, you have a right-hand side, and then there's an organization where the left side of the tree is the lower values, the right side of the tree is the higher values. A heap, you are always either going to be greater than or less than your children. So if you're a max heap, you're going to be a bigger value than your children. A min heap, you're going to be lower than your children. So trees are typically going to be using a pointer tree node structure to organize this, where the heaps, we're going to talk about them being implemented as an array. It's not to say you couldn't build them using pointers, but an array works out really, really well for heaps because we normally have a heap, as we said, of a fixed size. We want to keep track of the top 100 trending things. We don't need to worry about bigger than that. We just are fixed on that size. And we'll talk about how we can do that. It's a really cool set of algorithms. And so the great thing about a tree is I can organize the entire data into a structure where I can find anything relatively quickly. When I know everything less than me is on the left and greater than me is on the right, well, if I want to find something, I go left or right. When it's min or max, those are easy to find in a heap, but a value somewhere in the middle could be anywhere in the heap. It could be anywhere below me. So it's not exactly easy to find things in a heap. So just remember that there's some similarities to trees that we're going to talk about, but they are not trees. All right, so heaps are really super, as I said, foundational to a lot of computer science. We're going to use heaps for sorting. Obviously, we're talking about it within priority queues. If you get to the point of studying graphs in detail, there's Dijkstra's algorithm and some others that use heaps to help organize the way we path navigate through a graph. It's kind of like driving on a map, if you will. They help to merge sorted data or even order some statistics, amongst other things. There's just a few samples inside of there. So heaps are really useful and important to know about. And we're going to get a chance to play with them a little bit, maybe not as much as we would like given the time we have, but we are going to get you familiar with them and give you enough to be able to study them further in the future as you need.